Let us start our class. So in the last class, we spent time looking at the energy and what is the expression of that. We took an example, and then we spent a good amount of time on electric field in matter, where we discussed about how a conductor behaves under the influence of an external electrostatic field, and how an insulator behaves. And remember, both of them were neutral, so they were under equilibrium. And then we also looked at the relative permittivity, where I have explained the relative permittivity is actually epsilon r, which is derived from electric susceptibility. And this electric susceptibility is nothing but it is coming from the property of the material, that is how it behaves with the electric field. And if we substitute in our electric flux density, we end up with a vector called P, which is called as a polarization density vector. And then we also talked about the dielectric strength, that is the maximum electric field that an insulator or a dielectric can tolerate without breakdown. Because once the electrons which are tightly bound with the nucleus are gone, that means the dielectric material will no longer be holding the dielectric properties, and it will be becoming a conductor. Okay, so this is all what we did in the last class. So now let's move ahead, and then let's define the currents and the current densities. So we know it very well that if you have an area across, so I'm taking this as a cross-sectional area. Okay, it is of any shape, and its area is S. Then if I have a current density, or before current density, so if I have a current, then the current which is passing in a given area, so the current is nothing but, the current through a given area is nothing but it's an electric charge passing through that area per unit time. This definition, we know it very well. I is equal to dq over dt. So in electromagnetics, what we do is, rather than working with current, we mostly work with current density. So that's why we are introducing a concept of current density, J, which is ampere per meter square. That means it is actually, you are normalizing the current with respect to the cross-sectional area. That is nothing but your current density. So if this is the same closed surface S, and now I'm not talking about current, I'm talking about the current density, which is a J bar, it's a vector. So when the current density is passing here, then how much is the current density passing through the surface area is nothing but the dot product of that. And therefore, if you integrate J bar dot product with this cross-sectional surface, we get what is called as the current passing through this surface, passing through this given area, which is S. Okay, so this is the definition of current, and this is the current density. And this current density is actually a conduction current density. This is called as a conduction current density. That means this is the current density, which is because of now charges, electric charges, which is passing through. Okay, so it is because of the movement of the charges, or in a conductor, it is because of the movement of the free electrons. Then that kind of current is called as conduction current, and that kind of current density is called as conduction current density. Okay, so it is due to the charges being conducting in a material, and it is for conductors. This is the relationship. Okay, so the relationship is the conduction current density is proportional to the electric field. It is proportional to the electric field, or J bar is equal to sigma E, where sigma is called as the conductivity of the material. It is called as the conductivity of the material. So this is the relationship that we are going to use now throughout this course and even, in electrical engineering. That is, the conduction current density is proportional to the electric field and the proportionality constant is the conductivity. So J is equal to sigma E. And this is actually called as the Ohm's law in point form. Then besides this conduction current density or conduction current, you have another two types of currents. One is called as the convection current and another is called as the displacement current density. So this displacement current density, we will leave it for a while because we will cover it maybe in, chapter 8 or chapter 9. But let's just quickly talk about convection current. So what is a convection current? Again, you might be aware of this because in physics, you might have studied this. It does not involve, movement of charges. That is, it does not involve any conductors. So you do not require a conductor for current to pass through, because in conduction current density, you require a conductor. So without a conductor, the current cannot pass. The conduction current cannot pass because conductors can have free electrons, and that free electrons allow to move through the conductor, therefore for giving rise to what is called as a current. But here it's not the case, and therefore it doesn't satisfy Ohm's law. A very simple example of this convection current, just for you to visualize, is when the current flowing through an insulating medium such as gas or vacuum or liquid. This is your convection current. A very good example is a beam of electrons in a vacuum tube. So you have a vacuum tube and the beam of electrons is shooting from one end to the other end. So that beam of electrons is called as the convection current. Okay. So how do we represent convection current? Again, convection current is a vector, and if this flow of charge, that is the beam of electrons, is nothing but your charge. If that flow of charge has a density of rho v, coulombs per meter cube, and this charge is moving at a velocity of u in any direction. For example, I'm showing it in the y direction because now velocity is a vector. So I'm showing it in a y direction, uy, ay. Then the convection current density is simply given as the multiplication of the total charge and the velocity. This is called as the convection current. So two types, conduction current density and convection current density. So conduction current is because of the flow of charges in a conductor, and convection current density, it is also the flow of charges, but mostly in an insulator. So these are the two definitions, and in our course, we are mostly concerned about the conduction current density. So let's take an example. This is the example which is done in the textbook. You can also have a look at the textbook. So where first they define the convection current, and then they defined the conduction current. And then this is the example, which is the Ohm's law. Now, what is the example? The example is saying that you have a conductor, and this conductor is of length L. Okay, so let me make it bigger. It's of length L, and it has a uniform cross-sectional area. So the cross-sectional area is uniform, which is S. Derive Ohm's law in circuit form. So now we have to derive the Ohm's law in circuit form because this conductor is connected to a voltage source V0. Okay, so now what do we know if it is connected to a voltage source? Then we know that the conductor will now be conducting, and therefore there will be current passing through it, and the direction of the current is this direction. So in that case, what will happen? You will have an electric field which will be created here, and the electric field will be from the positive terminal and going towards the negative terminal. This will be the electric field. And because of the electric field, you will have the current density, or the other way around. You can think of the other way around, because if the current is in this direction, then the current density J bar, the conduction current density, will be in this direction. And because conduction current density is proportional to electric field, so therefore your electric field generated will also be in this direction. So now let us go and first find what is V0. So what is our V0, which is nothing but the potential difference. That is the potential difference of this point with respect to this point. The potential difference is equal to, I'm just going and looking at the expression that we got for the potential difference, which is equal to minus integral A to B, that is point A to point B, E bar dot DL bar is equal. This is the expression. So here we are also now integrating. So we are now integrating this electric field E bar over this length L. And this is our point, the 2 points. Now we are integrating it from point A to point B. Now remember one thing, guys. So whenever you want to integrate anything which has kept at a potential difference, which is kept at a potential difference, one is at lower potential and one is at higher potential. Whenever we do the integration, we always integrate it from the lower potential to the higher potential. We always integrate from the lower potential to the higher potential. So this is kept at lower potential and this is kept at higher potential, right? See, this is negative and this is positive, lower potential, higher potential. So if we integrate it from lower potential to the higher potential, then what will happen? We will end up getting this term as positive because minus is there. But since we are integrating from lower potential to the higher potential, that is in the direction opposite to the electric field, that's why we will end up with minus of minus becoming plus, and then we will get the potential difference as positive. And now here it is E bar dot DL bar. My DL, this is my length L, this is my DL. Okay, this is my DL, and since my since my electric field E is uniform, so therefore E bar dot DL bar will nothing but it will become simply the electric field multiplied by the length L, and even my length L is straight. So that's why it's a straight wire of uniform cross section. That's why this dot product will become simply multiplication of E and L. And therefore, since the potential difference V naught is E multiplied by L, so therefore the electric field magnitude will be just V naught over L. Now, what we are doing is, see that this is the note which I have written it, and I have just now emphasized. That is, the integration of the electric field is always performed from the lower potential to a higher potential. So lower potential is A, higher potential is B. So this A in the expression is the lower potential, to the B in expression is the higher potential. In our case, this is the lower potential and this is the higher potential. Now we are finding the conduction current density. So since we got E, so the conduction current density J is equal to sigma E bar. I'm dropping the vectors. I'm working with the magnitudes because we want to get the Ohm's law in circuit form. So J is sigma E, which is equal to sigma. Just now we got E, which is V over L. And Now I'm finding the current. So my current is nothing but, the current which is passing through here is nothing but, it is the J bar, which is integrated over this cross section of this wire, which is S. So it is integral of J bar dot ds. But since our cross-sectional area is uniform, it will be just simply J multiplied by ds. So the integral over J bar dot ds bar over the surface will be just J multiplied by S. And now if we substitute J, which is this one, multiplied by S, and do some rearrangements, we will see that V0 will become L over sigma S times I. And what is L over sigma S? The L over sigma S is nothing but the resistance of the wire or resistance of this conductor. See, R is L over sigma S. So this is the resistance where R is equal to, we can represent R in two manners. So here R is equal to L over sigma S. Sigma is my conductivity of the material. That means this is a property which allows you to know how good your conductor is able to, conduct current. And we know it very well that conductivity is 1 over rho C. Rho C is the term which is used in our book, and this represents resistivity. Resistivity. And again, we don't know this very well. We have already been using the conductivity is nothing but it is reciprocal of resistivity. So conductivity is a property of a material. Therefore, you can also think that resistivity is not also the property of the material. So this is how well it conducts the flow of charges, how well it stops the flow of charges. So if this is the expression, then in terms of conductivity, it is L over sigma S, or in terms of resistivity, it is rho C L over S. And this expression is not new to you. Remember, this is the expression of the resistance of a wire with uniform cross section. Wire of length L with a uniform cross section. R is equal to rho C L over S. So this is the resistance. And therefore, we are ending up getting the ohms. Now, what we have to remember is, this Ohm's law that we derived. This is the Ohm's law for, all these conditions. It's a uniform cross-sectional area S, and that's why, that's why you are able to apply, the Ohm's law, and you are able to find R as L over sigma S. So this is what I'm writing here. This equation is useful in determining the resistance of any conductor of uniform cross section. So this expression can be used for any conductor with uniform cross section. But if we have a conductor which has a non-uniform cross section, then we have to go and we have to apply the general expression. Now, what is the general expression? R is equal to the potential difference over the current, and the potential difference expression is nothing but it is the integral over the length of the conductor E bar dot dl. That is again going from lower potential to higher potential. What is the current? Current is nothing but integral over the surface conduction current density J bar dot ds. J bar. So instead of J bar, I am writing sigma E bar dot ds. So this means that if you know the electric field, and if you know the conductivity of the material, and if you know at what, say, uh, uh, potential difference it is maintained, or even if you don't know the potential difference, if you know the length, then you can use this expression to find the resistance. Okay? And in a similar way, we can also find the power. So power can be calculated as the rate of change of energy, W, or force times the velocity. So if you see here, this will be the expression that you will end up with. So the power is equal to integral over the volume E bar dot J bar dV. So this is responsible for the current. This is responsible for the potential difference. So I have not derived the expression for this one, but if you want, you can go and look at the textbook because of our time constraint. So here the complete, derivation is there. Because of the time constraint, we would not be able to do it. But if you want, you can look at the textbook. So this is what we will get, expression. And for the present problem, this expression will end up with E multiplied by J, which will be nothing but VI. So it will be integral over the volume. So integral over the length of E will give me the potential difference, and over the surface J will give me the I. So this is called as VI. And again, this is only possible for a uniform cross section. Otherwise, you have to go and use this general expression. So this is how we derive the same Ohm's law, which we have been using from the last, I think, 2 or 3 semesters in various courses, and we studied that in electric circuits. But here we are now trying to go a little bit deeper to see what is actually the reason of getting this Ohm's law. And the reason is our electric fields and the magnetic fields, because you will see that the current is coming from the it is from the electric fields, and then you will also see that current is also responsible. Magnetic field is also responsible for currents, but that will be later. But as of now, this is how we get the Ohm's law. Now, there is one more small topic. So if you see in the textbook, so after the Ohm's law, see there is some examples on the Ohm's law. Please, have a look at that. And then here also another example, have a look at that. The dielectrics, we discussed about this dielectrics, but this section is not covered. Only selected expressions are covered. So this expression and this expression and this expression, which I discussed that. The dielectric strength we discussed. This section is not included in our course. Please refer to the syllabus. Okay, please refer to the syllabus. In the syllabus, we have mentioned which sections are excluded from our syllabus. And what this one? Yes, this one. So which is called as the continuity equation, or it is also called as the current continuity equation. So this is a very small topic, and we actually want to we are not going to derive the complete thing. We are just going to discuss about this, because we are going to use this current continuity equation in our subsequent chapters. So what is the current continuity equation? So we have to just think about it. It is saying that if I have a closed surface S, so suppose this is my surface S, which is closed, not open. Okay, so you can think A simple example for us to understand is you can think it as your soccer ball. So your soccer ball is a spherical shell. So you have a soccer ball, and then what it is saying is that the net current I leaving this closed surface S can be expressed as this. So it says that, so from the soccer ball, if you think that how much is the current coming out of the soccer ball, leaving the soccer ball, is nothing but closed surface integral J bar dot ds bar, is nothing but closed surface integral J bar dot ds bar. So if this is your closed surface, then the amount of current coming out of it is J bar dot ds bar, and J bar is the current, the conduction current density. Though the conduction current density, you can think it as everywhere, the conduction current density. And it is a closed surface because we are doing the surface integration on the closed surface, like your soccer ball. And then it is saying, and then this is equal to minus dq over dt. This is the current continuity equation. This is equal to minus dq over dt. That means it is saying that the amount of current which is flowing out of a closed surface, that is out of the closed soccer ball, is nothing but inside it must be equal to the rate at which the charges are depleting with time. So it is minus dq over dt. It is equal to the rate at which the charges are depleting inside the closed surface. So if we, so let's look at this small, it's not a derivation. We just trying to represent a Q with other term, and let's do this, and then let's think of it a little bit more. So this is my d minus dq over dt, where what is this Q? Q is the net charge which is contained in S. So Q is nothing but the charge which is inside that spherical shell. So now if you just, think about it. If you want the current, you are integrating the current which is going out of a spherical shell, and inside you have the net charge Q. Then if the current is going out, then inside this net charge should start depleting, right? Because it should be depleting with time, because dq over dt is your time, is your current, sorry. So if you outside, if the current is going, then inside the rate at the charge should deplete with time, then only this will satisfy, if you just think about it. Or you can also think in the following way, that if you have the current density everywhere, the amount of current density outside, which is leaving, outside your soccer ball, which is leaving, must be equal to what is inside. That is, what is inside means what is entering the spherical shell must be leaving the spherical shell. So this is what the current continuity equation is saying. So here what we are doing is the closed surface integral J bar dot ds bar is minus dq over dt. Now charge, we are trying to represent it with a general expression, which is nothing but rho v, so integral over v, rho v dv. Rho v is nothing but the charge density for a general expression, charge density over a volume. And now what I am doing is this particular equation, I'm now trying to represent it in this manner. So I am replacing the surface integration with the volume integration. So how can I replace surface integration with a volume integration? Yes? closed surface integral j bar dot ds bar. How can I represent it? Should I represent it with which theorem? Yes, integral over the surface
Stokes theorem.
field, any vector field a bar dot ds bar is equal to integral over the volume, the divergence of a bar over dv. Which theorem is this? Yes,
Divergence theorem.
this is the divergence theorem. Yes, this is the divergence theorem. So as I told you, divergence theorem allows you to relate surface integration with volume integration. And you have another theorem, which is Stokes theorem. Stokes theorem. So Stokes theorem relates the, yes, it will relate the line integral to the surface integral. So here we are applying the divergence theorem. So closed surface integral j bar dot ds bar is integral over the volume. The divergence of j bar over dv is equal to this as it is. Okay, so that means this is wrong. I will correct it. So it should be divergence theorem. It is from the divergence theorem. Okay, then after this, what I'm doing, I'm just looking at the right hand side, and on the right hand side you have the differentiation with respect to time, and you have integration over the volume rho v dv, and this I can bring this differentiation inside, and I'm getting it as minus integral over the volume dou rho v over dou t, or if I equate inside the integrations, del dot j bar is minus dou rho v over dou t. So this is called as the current continuity equation. So this is the current continuity equation, which is the divergence of j bar is minus dou rho v over dou t. And this is derived from the principle of conservation of charge, and essentially states that there can be no accumulation of charge at any point. There will be no accumulation of charge at any point. So that means for a closed surface, whatever is going out in the form of a current, inside it should deplete, or if whatever is the charges which are inside your closed surface must be equal to the outside charges. I mean to say the current or the current density, whatever is inside should go outside. So I'm talking it with respect to time. Okay. So this is the current continuity equation. And if you have for the steady current, that means, if my time is, this differentiation is becoming 0 for a steady current, right? Because dou rho v over dou t will become if the current is steady, and then your del dot j bar becomes 0, showing that the total charge leaving a volume, it will be same as the total charge entering the volume, which is your Kirchhoff's current. Okay, so this is called as the current continuity equation. Del dot j bar is minus dou rho v over dou t. I know there is a derivation here and a little bit of difficult to say visualize, but just do your best, because we are not going to derive several such type of equations in our subsequent chapters. We are going to use the equations. So this is called as the current continuity equation. And this is one more small thing which is trying to tell us that if you have, so here what we are trying to do is we are trying to do the following. We are trying to use the Ohm's law, which is J bar is sigma E bar, and Gauss's law. I'm just writing the Gauss's law of differential form in terms of E rather than D. So this D is epsilon E bar. So epsilon I am taking it here. So del dot E bar is rho V over epsilon, and J is sigma E. Okay, and this current continuity equation, del dot J bar is minus dou rho V over dou T. If I take these three equations and if I use and if I substitute, one equation in the other equation and simplify, then I will end up with this kind of homogeneous linear, single order differential equation, which is dou rho V over dou T is equal to minus sigma over epsilon times rho. Okay, that means in this J, you first substitute this, and in E, you just substitute this, and then do some simplification, you will get this. And the solution of this homogeneous linear, the first order differential equation is an exponential. So that means your rho V, which is rho V, which is the variable that you want to solve, is equal to rho V0 e power minus T over capital TR. So where capital TR is epsilon over sigma, that is the permittivity over permeability. And this is called as the relaxation time or the rearrangement time. And rho V0 is the initial charge density, that is the charge density at time t is equal to 0. So what this is, this equation is telling that the above equation of rho v shows that an introduction of charge at some interior point of the material results in a decay of volume charge density rho v, and associated with the decay is the charge movement from the interior point at which it was introduced to the surface of the material. Hence, most of the charges vanish from the interior and appear on the surface as surface charges. So what this expression is saying, this is saying that on a conductor, okay, so which is this conductor is already conducting, okay. That means if there is, it's, if it is connected to the potential, and when the charges are already, it is not, so let me put it in a simple way. If it is not in equilibrium, okay, when the conductor is not in equilibrium, and in this case, so it will not be in equilibrium, that means you are giving extra charges, and this extra charges can come from connecting it to a potential difference or potential source or anything. In this way, if extra charge is given to it, then what will happen? This charge, wherever you give in the conductor, inside the volume of the conductor, wherever you give, what will happen is your conductor will rearrange these charges, and in such a way that most of the charges will appear only on the surface. So if you see here, what I'm trying to say is, in your conductor, if this is my rod, and this is in equilibrium, but once it is connected to the potential difference, then in these case you are injecting more charges here. So when the more charges are injected, then what it is saying that, if this is the thickness, then maximum charges will only go to this surface. So the maximum charges will be only available at the surface, and inside you will not see anything. So most of the charges will move to the surface and create what is called as surface charge. So they will all move along the surface, not inside. So here they will not move. And even if your voltage source try to put a charge here, then within no time, within that relaxation time, this rearrangement time, this charge will quickly move to near the surface and then flows through the surface. So most of your charges will be here, like this. And this is coming from this expression. Okay, and this is called as the relaxation time or the rearrangement time. Epsilon over sigma. And remember, here everything what we are talking about is for the conductor. So therefore, sigma is the conductivity of the conductor and epsilon is also the permittivity of the conductor, because I know here we are considering not a perfect conductor. So because if a conductor is not perfect, then sigma, the conductor will also have a permittivity. So that will give you this TR, which is relaxation time. And for conductors, this relaxation time is very, very small, 10 to the power of minus 19. So the instant, the charge enters the wire center, within an instant, it will be available at the surface. But for dielectrics, it's not the case. For the dielectrics, wherever the charge is inserted in the dielectric, the charge will stay at the same place for long time, for very long time. Okay, so when your dielectric is now, it is neutral, it is in thermal equilibrium. It is in equilibrium, and then if you put some charge on it, and if you try to put that charge inside it also, that charge will stay at there, for very long time. So this is the difference between the dielectric and the conductor when they are given extra charges. That means they are no longer neutral when you give extra charges. So this is the current continuity equation. Okay, so we are going to use this expression in our later courses. Now we will go and take the last topic of our chapter number 9, which is the boundary conditions. Very, very important boundary conditions. So here our main objective is to try to find if my electric field is in free space, and suppose all of a sudden the free space finishes and then another medium starts, and the other medium can be plastic, another medium can be conductor, another medium can be wood, or another medium can be some other material. So in this case, how would the electric field behave? What will be what will be experienced by the electric field? This is what we are trying to see in the boundary conditions. Okay, so will the electric field will pass from the free space to the wood as it is, or something happens, or it will lose some energy, or it will change direction, or with its magnitude changes? This we are trying to find it. Okay, so first what we are doing is, here if you see, this is our problem statement, and in this case what we are doing is, this is my x-axis, and I'm assuming that this is one medium and this is another medium. Okay, medium 1 has a permittivity of epsilon 1, and medium 2 which has a permittivity of epsilon 2. And suppose an electric field is going, the electric field is going from medium 2, so this electric field is E2, and then it will hit the boundary. This is the boundary. So my x-axis will be the boundary. Or if you look at in 3 dimensions, the xz plane will be my boundary. And then it will hit the boundary and the field will continue moving. That is, here the field I'm naming it as E1. So our objective is, will E2 be same as E1? This is what we want to know. If it is not same as E1, then what will happen? Will all of it, because electric field is a vector, so it has x, y, and z component. Will all the 3 components get affected or only some components get affected? This we are trying to find. So this is our medium 1, this is our medium 2. Now this is my electric field E2, this is my electric field E1. Now what I'm doing is I'm trying to make a small closed loop here near the boundary, so that half of the loop is in medium 1 and half of the loop is in medium 2. And I am and I'm deciding the length of the loop as delta x and the height of the loop as delta y. And now I know that the closed line integral of an electric field must be equal to 0. I know this rule. I know this law. And an electrostatic field must satisfy this law, irrespective of whether it is in medium 1 or medium 2 or half in medium 1 or half in medium 2, anything. This has to be satisfied. Any vector field which doesn't satisfy this is not an electrostatic field. So therefore, even if your loop half is in medium 1 and half is in medium 2, still it has to satisfy. So now we are applying this expression here. So that means it is made up of integration of line 1, line 2, line 3, line 4. So 4 lines will become my closed loop. And I'm integrating in this direction. Okay, that's why I've put an arrow here. You can do it in whichever direction you want. So now tell me, from this 4 lines, you know, how many line integrals will become 0? How many line integrals will become 0?
2 and 4.
Yeah, this is under the condition that, I am making my delta y, I'm making this height goes to 0. I'm making it small, 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 and almost negligible, so that the 3 and the 1 line will be almost touching the boundary. So as delta y tends to 0, which line integrals become 0?
Three and 1.
Yes. So when delta y tends to 0, which line integrals become 0? Your 2 and your 4, because the height, this is almost going to 0. So your 2 and 4 will become 0 as delta y tends to 0. So only left is 1 and 3. And therefore for 1, just give me a minute. Therefore for 1 and for 3. So for 1 is this integration. And if this is my delta x, that means if I assume this as x, this will be x plus delta x. And this is only in the x direction. That's why we can only do the line integration with the x component of my electric field E2 and electric field E1. So E2 will be E2x dx, E2x dx, and from here to here, if this is my x and this is my x plus delta x, that means from x plus delta x to x, x plus delta x to x, E2x dx. And then here, since I'm doing in this direction, so here from x to x plus delta x. So x to x plus delta x. And what is the electric field here? E1. So the x component, E1x dx. And now since our delta x also, you know, is, if you do the integration of this one, I will get is E1x delta x minus E2x delta x, because our delta x also, we are considering it is very, very small. So therefore, integration is mere multiplication. And therefore, if you bring one term on the right-hand side, you will get as E1x as E2x. Okay, so we will stop here. And then in the next class, we will continue with the boundary conditions. And any